We're gonna get started today on the next system, which is gonna be the skeletal system, and we're gonna see this one starts to become a little bit more involved. This is to me where AP1 starts to get a little bit more depth to it in terms of the amount of physiology taking place. So you can see we have a few key questions that we're going to be kind of concentrating on. This first one here is a little bit more about bones and skeletal organization as well as bone classifications. We will get into how bones are made, how they're maintained, what are the things that regulate that, and again, some of those homeostatic mechanisms as we get further along in here. So the first one again here, how are the bones in the skeleton organized, is really looking at kind of bone classifications, bone structures. So first off, let's just talk overall a little bit about what is the skeletal system doing for the body. So the skeletal system is kind of the bones, tendons, associated structures like ligaments and that. You can kind of talk about those as all being part of the skeletal system. In terms of function, again, a few very obvious ones. Without the bones, we don't have any support to the body. We don't have a structural system holding the body up. The bones hold the weight of the body when it's standing up. They hold different tissues in place, things like the teeth and the jaw, as well as other organs in place. I think everybody's pretty aware your skull is protecting the brain, your ribs and sternum protecting the heart and lungs, vertebrae protect the spinal cord. So again, like a lot of connective tissues, providing protection for the body. While the skeletal system in and of itself does not do the movement that is the muscular system, the bones do provide the lever system that is going to let those muscles bring about particular movements versus just a lump of tissue getting shorter or longer, which if we didn't have bones, that might be a little bit more the case. The other two are the ones that sometimes people don't think about as much, is that the skeletal system is providing a lot of storage for nutrients in the body. So calcium is a big component of the salts that make bone hard. 99% of the body's calcium is stored in the bones. A good portion of the phosphorus is stored in the bones. Also, as you get to be an adult, the marrow cavities in certain bones that are called long bones tend to be filled with adipose tissue. And again, another spot where we see this. Finally, that red bone marrow that you see at the ends, if you've ever heard of a bone marrow transplant or anything else like that, our bone marrow, the red bone marrow specifically, is blood forming cells. These are basically what are called hemocytoblasts, which are blood stem cells, and that is where all of our components of our blood are made, are actually in the heads of the long bones and a lot of these short and other bones that are present in the body. So hematopoiesis is this idea, or hemopoiesis, depending on which book you read in that is what you'll see as the term that talks about this blood cell formation. We can see when we're looking at bones, and this is one of the few times I would say in A&P where the classification system is a classification system that makes 100% sense. In terms of the different types of bones, you have bones that are much taller, so things like your forearm bones, for example, much longer than they are wide. You can say the same thing with the humerus, femur, whatever else. Most of the limb bones would be this case. These are what are referred to as long bones. So longer than they are wide, extended ends at the ends, these heads of the bone. Even the finger bones, like I said, are considered long bones because they are longer than they are wide and have expanded ends at the tips. They're called long bones. Ones that are about the same height and width, which are really your wrist bones and some of the bones of the ankle. These are called short bones. Like I said, easy so far, right? Some good examples of long bones, like I said, extended at the ends, longer than they are wide. Some also examples of short bones, so the carpals and tarsals. We also have a lot of bones like our skull bones, our sternum, the scapula. These are very thin, flattened bones. They are called flat bones. And then the last one here is, does it not fit any of the other classes? So it's not short, it's not long, it's not flat. Well, that one's kind of weird. It's irregular. And those are the four main classes here. So weird shapes that don't fit in the other ones here, things like your vertebrae, your hip bones, the sphenoid bone, which looks like a bat, so bat bone there. These are all considered to be irregular bones. Sometimes you have more roundish bones. They might call sesamoid bones. So things like your kneecap, for example, your patella. So you can sometimes see some other classes in there as well, or sometimes they'll talk also about sutural bones, the skull bones, because they are stuck together like this. They call them sutural bones sometimes. So sometimes you see more of outside of these 4 classes, but again, mainly 4 classes here. What I would say on these ones is really easy. A question to ask is, okay, here is a vertebrae. Which class of bones does it fall in? Is it short, flat, regular, flat, long bone? Easy question to ask, something like that. So these show you some of those flat bones. So like I said, sometimes the skull bones will talk about being sutural bones. Some of the other irregular bones here, if you're looking at like the vertebrae, the ethmoid bone, which would be up in the top inside of your nasal cavity, sphenoid. The other thing I would say about bones, and to me this is always one that's kind of surprising. I don't know if I'd say surprising, but the main thing is a lot of times when you look at bones, they seem like they're unchanging because really when you think about fossils, what generally fossilizes, it's the bones. They have a lot of these salts in there. They're very hard. They don't decompose as quickly, so they tend to be the last thing that sticks around on an animal. If that animal becomes fossilized, these are generally what become fossilized. So a lot of times when you see bones, they look like they're unchanging things here. In reality, bones have a lot of blood supply to them, have a lot of nutrients going into them. They are a very dynamic tissue made of a number of different are very dynamic organs made of a number of different types of tissues. So you have that bony tissue, but there's also going to be a lot of fibrous connective tissue. There's cartilage on the end. There's a good blood supply. There's lymphatics. There's adipose tissue. There's nervous tissue, nerves going into these bones. And again, very dynamic, almost always changing. We're going to see that a good portion of our bones are kind of reconstituted each year, depending on where this bone is at. Some not as much, other areas quite a bit more often. And the picture on the lower right here is just kind of showing you this structure of the kind of long bones microscopic structure, which we'll get into on the next slideshow probably. So the outer part of this bone, so this thick, dense part, so if you were to cut a bone in half and look at kind of the outer portion of it right here, this is referred to as compact or dense bone, cortical bone sometimes. Though that is that compact bone. The inside here, and also in a lot of the heads of the bone, you'll get this little kind of branching, looks like a lot of these, like if you think like a railroad bridge or something with all the little triangles, it looks a lot more like that. Those are trabeculae, and those make up what is called spongy bone or a calcaneus bone, cancellous bone, excuse me. And again, these things are always changing. It is, like I've said a couple times already, a very dynamic, changing tissue. You are remodeling this to deal with the stresses put on it almost all the time. And this shows you a little bit better. So you can see the compact bone along the outside here, that compact or cortical bone, the spongy bone, which in a way does look a lot like a sponge in the head of the bone, the long bones. We'll see on short bones and some of the other ones here, this compact to spongy bone layout might be a little bit different. But again, the structure is similar in those ones in that the compact bone has the same microscopic structure as a spongy bone. Again, same microscopic structure when we look at a short bone versus this femur here. And this is kind of showing you those trabeculae in here. This is some decalcified bone with osteocytes in it. We'll talk about a lot of the structure as we go, where you can see these are the bony trabeculae in the spongy bone and a lot of adipose tissue actually in between. So really one of the few things, last thing I'm going to talk about here is a little bit about microscopic structure. You're going to see that there is certain types of bone cells that are present. We're going to see that in reality there's 3 types and then the bone stem cells. So osteoprogenitor cells, these are going to be those bony stem cells. So osteoprogenitor cells from mesenchymal connective tissue, that undifferentiated connective tissue, these are going to mature to become things like osteoblasts, osteocytes, osteoclasts. All 3 of those other subtypes are coming from these osteoprogenitor cells. So we're going to see that we really have 3 main types of adult bone cells when we look at this one. So osteoblasts, if you remember fibroblasts or chondroblasts, those were those building cells. So osteo, when we put that osteo prefix in front of it, now it's bone. Blast is a building cell, so it's a bone building cell. These are going to be cells that are actively laying down fibers and what is going to be called osteoid, that matrix that will later calcify and become the hard bone. That is what the osteoblasts are making. It can be found along the inside and the outside of the bone, actually. Osteocytes, these are going to be the cells that once they get trapped in that osteoid, they are within the inside of it, they are mature cells at this point. So they are bone cells, not bone building cells, bone cells. They maintain it, provide nutrients to those areas, help maintain the matrix there, can be triggered to make new bone if need be. And they're definitely detecting stresses on the bone and helping to remodel the bone. The third type here is the osteoclast. We haven't really talked about clast cells yet, but the main thing with the osteoclast, we have a bone building, a bone maintaining. Not surprisingly, we have a bone breaking down or a bone reabsorbing cell. So osteoclast can release a lot of different types of, it's actually some acids that can help reabsorb the bony matrix. These are more often found on the inside of the cells, in the inside of the bones and along that endosteum. But the whole thing here is these have these enzymes and acids that can help reabsorb this bone. And we're going to see they make a little pill when they do that called reabsorption lacuna. But the main thing is with the remodeling the bone, we definitely need sometimes to reabsorb that. The other thing we're going to see is because we store a lot of calcium and other minerals in the bone, one of the ways to free those up is to reabsorb some of that bone. So if calcium levels get low in the body, a way to actually bring calcium levels back up, or excuse me, in the bloodstream, the way to bring them back up is to actually have these osteoclasts reabsorb some bone and make that calcium that was stored away, put in the warehouse, available to take back out. And this is just kind of showing you the different images of some of these ones. I do want you to know what osteoblasts do, what osteocytes do, what osteoclasts do. I'm not planning on showing you slides and making you identify osteoblasts versus osteoclasts. But you do need to know what each of these cell types are doing and how they would play a role in, as we get to it later, things like calcium, blood calcium levels, for example. The other parts of the bone are going to be that matrix, that osteoid. So this is going to, we'll see, is really organic and inorganic components together going to make this up. So about 1/3 of these are organic, and those organic components are stuff we've talked about already. These are collagen fibers. So these collagen fibers are really good. They add that tensile strength, give that bone some flexibility and ability to resist stresses on there. Again, if there wasn't enough organic components here, bone becomes actually quite brittle. There is a disease called osteogenesis imperfecta, where your body does not make collagen fibers correctly, and that disease is also referred to as brittle bone syndrome. So again, if you don't have the collagen fibers in there enough, the bone does not have its normal strength and durability. The other 2/3 are going to be inorganic. So these inorganics are a couple different calcium salts that go together. So calcium phosphate and calcium hydroxide, when these two salts interact, they become something that's called hydroxyapatite. This is what gives bone its hardness. When you think about bone and its density and that toughness, when you hit on it, that ability to kind of not get compressed or really to bend much at all, it is this hydroxyapatite that provides that. It calcifies this matrix, makes it quite strong. And again, the inorganic to organics need to be correct. If we don't have enough organic components, enough protein, enough of those collagen fibers, you get really brittle bones. If you don't have enough calcium, you get very bendable bones, so these kind of soft bones. And we'll talk about this with nutrient deficiencies, but sometimes when you don't have enough vitamin D, people that are very, very vitamin D deficient in certain countries, if you've ever heard of the disease rickets, this is this really kind of leg bones and that don't support weight well and get bends in them because they are lacking sufficient calcium in the diet. Again, it has to be the right components to these ones. Too much or too little result in bones that don't do the job we need them to. So to kind of build all this, we are going to, early on with these bones, you're going to have this kind of background stuff here. We secrete this osteoid. Those calcium salts interact, and that hydroxyapatite crystals get deposited around these cells. Again, we need a lot of nutrients in order for this to happen. We'll talk about it later on, but vitamin D ends up being very important for this because vitamin D is involved in being able to absorb calcium from our diet. No vitamin D, you don't absorb calcium from your digestive tract. Vitamin C, really important in collagen formation. If you don't have enough vitamin C, you don't make correct collagen. So if you're vitamin D deficient, if you're vitamin C deficient, both of these things are going to give issues with being able to form bone correctly. And again, definitely need enough calcium and phosphates for those salts to form. Again, when we reabsorb this bone, we release a lot of those substances there. We have different enzymes that will digest the organic and inorganic components. The acids really are getting the minerals freed up, and again, this may happen when blood levels of things like phosphate or calcium get low. One of the ways to bring those levels back up is to have those osteoclasts digest some bone to make it available to the rest of the body. And this just shows a fun one here, taking a look at the tibia. And on this one here, it kind of gives you the idea that there is a kind of rubbery background matrix in here. So this is a bone, obviously, that's been demineralized and had its minerals removed, but left all the organic components. You could actually do this with a chicken bone if you keep putting it into vinegar over and over again. The acid in the vinegar will leach out the calcium and will actually allow you to get a bendable chicken bone. But this is again showing that demineralized bone here. So what we'll look at next time is walking through a little bit more of the microscopic structure of compact and spongy bone and how that plays a role in how the bone works. I'll see you next time.